last year, many of you came and we had a big program on solar energy. And this year we are tackling the grand subject of electricity storage on the grid. And I just want to mention a few energy statistics, and I will have some handouts passed around so that you can be inspired about how big a problem it is that we are trying to tackle. It seemed like a big problem in 2002. Now in 2005, in light of the hurricanes and other issues that have emerged on the international stage, it looks like an even larger problem in thinking about the future of energy supply. I'm not going to get into the debate about whether we are or aren't peaking in oil resources. I think there's probably on the scientific side of the aisle people on one side and people on the other, and I'm not a geologist. Roger can weigh in. I think he's a are you a non-peaker? Roger's a non-peaker. So, but what we do know is that per capita, per person in the United States, each person in the United States is using something like 340 million BTUs of energy. And that compares to 13 million BTUs in India, and 33 million BTUs in China, and 48 million BTUs in Brazil. And we know that as those economies move forward, their energy per person usage is going to start to look more and more like the United States, and we know that that's not sustainable with the current selection of energy fuels and energy technologies that we have available today. If you add to that, and I will hand out a picture, just looking at it from the United States perspective, if you think about the North Atlantic Oscillation and you think about the predictions for global warming and sea level rise, and you think about how many facilities we have in the United States, the vast majority of all our energy production capabilities actually here where you're sitting on the Gulf Coast. And you think about how many hurricanes we're likely to have over the next 25 years. That could be a season like this past season. Again, it seems very unsustainable to have our entire transportation system based on one fuel, gasoline, that we have to manufacture in this area, that we are growing out of our current capacity, and that there is absolutely no alternative substitute for in this country used in any kind of commercial way. And so if any of you, those of you who are from Houston, had the experience I did Wednesday morning as I was moving one of my cars to the local garage where my husband has his office so that if we did have flooding in our neighborhood, I would only lose the one car in the driveway, that the other car would be up high, and I realized that all the gasoline stations along the route between my house and this office complex had plastic covers on it that said sold out. And there's no option. There's no plugging my car into the house and driving off the battery for a few hours until we get new gasoline supply. There's no buying alcohol fuel because I happen to have a Crown Victoria and they are, actually flex fuel dual use and nobody in the United States knows that, right? There's just no alternative. My alternative is to stay home. So we need to face that as a country and think about that, and we need to think about that in the face of the kind of regional instability we're seeing in the Middle East and the sort of cloudy future for Iraq and the kinds of political disruption we're seeing in Venezuela and the kind of statist policies that are emerging in Russia, that to have our entire mobility tied to the fate of regimes in countries where we cannot control what happens inside those countries. Really, it didn't make sense 30 years ago, but it certainly doesn't make sense today. And again, that's a good reason why we're gathered here today to think about what other kind of energy systems we could use that would at least diversify us so we'd have some kind of alternative if the worst were to happen. Two more things to think about. One is that if you look at standard projections from organizations, the Department of Energy, the International Energy Agency, all the big oil companies, they all put up these projections of how much oil is going to be needed in 2020 and 2030, and they all presume that OPEC will be adding something like 30 million barrels a day in 2010, and 2030 they'll be having to add 50 million barrels a day. And you have to understand the basic statistic, which is between 1979 and today, OPEC's capacity did not increase by anything of that order of magnitude. It actually fell from 39 million barrels a day down to 30 today. So we're expecting this organization of basically unstable countries in political transition to do something they have not been able to do over the last 30 years. And that seems like a very optimistic bet to say, yes, we're going to continue in the same path of mobility because these 12 countries out here that have never delivered in the past are going to miraculously deliver more oil than they've ever delivered in the past. And by the way, they're not making the investments now that would give us any indication that they intend to. And then the final statistic, if I haven't scared you enough, is that if you think about our situation in 1979 compared to today, in terms of energy infrastructure, like do we have enough infrastructure, you need to remember that in 1980, in the United States, our refineries operated at 72% of capacity. That meant that there was an extra 25%. If there was a crisis somewhere, we could take the oil out of the SPR and refine it, bring you the gasoline so that it doesn't have the plastic bag over the nozzle, right? In Europe, they were only operating at 63% of capacity. Same thing, you know, crisis today, bring the crude out of the stockpile, process it, gasoline to market. The comparative statistics are now 95% capacity. So basically, we are producing full out and refining in the United States, basically full out and refining in the United States. Something goes wrong, something as small as just a fire in a refinery has a market ripple, and building new refineries in the environmental atmosphere that we have in the United States and Europe and in the history of unprofitability of the business, coming up with more capacity to get back to this sort of 70% operations level, again, seems very optimistic. So that is the here and why of why we need to be thinking about alternative energy systems and looking at where nano and other advanced science can play a role. So with that, I'm going to turn the podium over to Dr. Wade Adams, who is our director for the Center for Nanoscale Science and Technology here at Rice.
Thanks, Amy. I've been at Rice for 4 years, and for 3.5 of those years, I have been swallowed up by the incredible whirlwind of Rick Smalley's vision for energy. And it's been a great pleasure to work with Rick for these 3.5 years to help develop this, the vision that he has shown us and shown the world and tried to get the nation to pay attention to. So Rick planned to have a bone marrow transplant roughly 3 or 4 weeks ago. It was kind of a moving target. And we were set up to do a video teleconference with Rick in his hospital bed. He was going to attend every minute of the lectures and participate by sending some vicious questions by email and probably asking a few by video himself. Well, it was not to be, but as Roger Anderson mentioned last night, I think Rick will be here anyway. I'm not sure that we'll hear his voice through the video conference, but the best we can substitute for that is to show about a 12-minute video that was taken of Rick at a birthday party for Neil Lane on the 1st of November in 2003. And in about a 12-minute clip, he talks about this energy vision that was still developing at that point. It wasn't quite as refined as it has been over the last 6 months or so, but I think you'll get a glimpse of what Rick was thinking from this 12-minute video. If we can just go ahead and roll that, and I'll be back after the video.
Thank you. I'll try to make this brief. I have been, as many of you know, on something of a personal journey for the past 1.5 years in a search for terawatts to find some happy answer to this problem we've been talking about. I believe the problem is simply stated that we have to find the new oil. The oil unquestionably was the basis of prosperity for this country and for the planet in the last century, particularly the last half of the last century. And it is very clear to me and many others, many in this room, that if oil remains the basis of prosperity for the world throughout this century that we're in, it cannot be a very prosperous or happy century for two reasons. One, we will certainly peak in worldwide oil production sometime in the early part of the century, perhaps very early, much sooner than we'd like to see it. But secondly, and most importantly, there are vastly more people on the planet now who don't consume energy to speak of that unquestionably will be consuming billions of more people as the century unfolds, consuming energy at the rate the top billion do right now on the planet. And it probably does turn out that we have a carbon wall with immense negative impact should we not find some way of getting around it. So we need to find an economic alternative to oil. The basis for energy prosperity for 10 billion people on the planet, that is our challenge. Now, I believe this challenge is vastly greater than what we have given it credit for. That between where we are right now and where we need to get to, so we really have found the new oil. I don't mean a liquid, I mean the technology that makes us energy rich again in an environmentally acceptable fashion for 10 billion people. Between here and where we need to get there are something like 10 major miracles. The good news is that miracles do happen. I've been involved in physical sciences long enough to see many of them happen. Lasers and high temperature superconductors and so forth. But at the rate that they've been happening over my lifetime, if I extrapolate in the future, beginning to appreciate the magnitude of the breakthroughs that need to happen, I'm not by any means convinced that we will get there soon enough. And so I believe that we ought to get much more intense about this than we have in the past and launch a major new energy research program and get this problem solved. So many of you heard me talk about this, and I want to just briefly talk about something that perhaps is new to you. In May, we had a wonderful workshop here on energy and nanotechnology. And we took DVDs of all the presentations. They're available if you're interested. And I have looked at these DVDs 5 times. I've attended the conference 5 times over and listened to everyone talk again and again. And even the people that I thought I understood what they were going to say from the very big moment they stood up, like Lorem Shoreham when he gave up. I find that even on the 5th time, I'm still learning things from this. And I've walked around trying to imagine at least one acceptable scenario for new energy by 2050 that seems to be consistent with the bulk of what people were saying. Now, there's almost certainly 3 or 4 different scenarios, but this is an interesting one, and I thought I'd just talk about this and then sit down. Imagine by 2050, where we've hacked this energy problem, what could it look like? Well, when we left oil as our prime energy driver on the planet, not only did we leave the best, cheapest primary energy source, this great gift from Mother Nature, but we also left behind the best possible way of transporting energy over continental and transoceanic distances. I mean, now that we're looking for an alternative way of storing hydrogen in our gasoline tanks, it's anywhere equivalent to the experience we have when we drive up to a Shell station and gas up with 300 to 400 miles of gasoline. We realize with what magnificent beauty gasoline was given to us. About 100 years ago, we found it, or the predecessors, the unrefined predecessors of it, self-propelled coming out of the ground. We got crazy rich on that. Now, you try to find some way of storing hydrogen that's competitive to that. There just isn't any. And when we go to get energy, primary energy from the Middle East or somewhere else and bring it across the oceans to the United States, the actual cost of doing that is really quite small. But when we leave oil, we've lost that. And so we're going to have a future where we're going to be bringing liquefied natural gas across the oceans. That's not nearly as efficient, and it's going to be terribly much worse when we try to bring hydrogen across the oceans. So how do we transport energy over long distances? Well, I'm imagining this scenario that the dominant way we transport energy over long distances is as energy. We don't cart it around in mass and reconvert it, but as energy, so electrical energy. And so if you had one word in this scenario to describe the new oil, it wouldn't be oil, it would be electricity. It wouldn't be hydrogen, it would be electricity. That is the key thing that makes things work. And so imagine for North America, for example, a continental grid, you know, all Canada and the U.S. and down into Mexico and down to Panama, electrical energy grid, which connects on the order of 100 million local sites. And the one characteristic that's most interesting in this scenario about those local sites is that at every site there is local storage. So not only did, when we left oil, did we leave the great primary energy source, we left the best way of transporting from here to there, we also left one of the best ways of storing energy. And the biggest single problem with electricity is storing it. And if we are to try to find a way of storing electrical energy on a vast scale, as we generate energy in gigawatt power plants and so forth, there's only a few options that you could imagine on that large scale for energy storage. But if you imagine attacking the energy storage problem locally, at the scale of a house or a small business, there must be many more technologies that are accessible there. I would rather fight the battle of energy storage locally than on huge scales. And it's fascinating what the impact of this is. If every one of those 100 million of local sites has their own local storage, which they locally have decided for their own particular sociological, economic, or whatever stupid reasons to use a particular technology to give them an hour of buffer or a day of buffer or 5 days of buffer, however long they decided to do it. Now the energy system starts to make a lot more sense because now the electrical grid can afford to be fairly erratic. The local sites determine just over what period of time they want to be buffered. To think of it as an uninterruptible power supply. And increasingly, the primary energy producers that put electrical power on the web can just simply dump the power onto the web at the cheapest possible rates, and locally, the local storage buys it off the web when it's cheapest, which of course is when it's most abundant. And no longer do you have to have a system as we have currently in the U.S., where we have almost, not quite, but almost twice the generating capacity than we use on average, because we have to follow the peaks and the loads. And perhaps most interesting about this is this local storage aspect about this system means that it will be very efficiently innovated continually by free markets, by technological innovation, because when locally a decision is made, well, we made a really bad mistake when we bought that energy storage technology from Sears. There's a much better one from GE these days. They'll agonize over it a bit, but after a couple of years, it wasn't the huge life-changing decision. It's a little mistake. And after a while, they sell off their old unit, or they can't find somebody to buy it. They just trash it, and they bring a new unit in. It's a small thing, but 100 million times small things gets to be very big. So this allows the electrical energy grid to transform itself with a time period of a couple years rather than time periods of decades, and gives you a tremendously robust source. Well, it's fun to talk about this, but what technology could give you that local storage? You can't buy it right now from Sears. What technologies would be necessary? Well, herein is some of the miracles of the sort that I'm saying that we need, and I'll talk about them in a moment. Just providing the local storage doesn't completely solve the problem, because you have a primary energy demand here that's going to have to come from new sources. I need one other key technology, and that is I need to be able to transform the efficiency of transporting electrical power over 1,000-mile distances, over continental distances. So instead of taking 100 megawatts over 1,000 miles, I need to take 100 gigawatts over 1,000 miles and do it cheaply so that I can afford to sell power at a couple pennies per kilowatt hour 2,000 miles away, paying for the entire infrastructure all along the way. If we had an answer to doing that, then things start to make sense. There's a fascinating, wonderful aspect about this. I've seen this it's next to the last point here. The mass primary power input to the grid from high voltage DC transmission lines can come from existing plants. So this is an energy system where you don't have to imagine, okay, we tear everything down we've got right now and build a completely separate grid. You can start putting this in place right now and have all existing plants providing power to the grid. But now you can hook in very remote sources, including vast solar farms in the deserts, where you're using the local storage to buffer from when the sun's up and when it's down, from when the wind's blowing, and wind farms to when it's not, going and importing vast amounts of electrical power from remote nuclear power sources way the heck in somebody else's backyard behind some military fence and done in some way you're absolutely sure there's no nuclear weapons risk associated with that. From clean coal plants, wherever we've found a place of putting them where we really think that we can stick the CO2 away and not have it come back at greater than 0.1% leakage per year. From remote hydro way up in northern British Columbia, stranded gas, waves, hydro, vast resources from far distance away brought into the grid. If you could make all this happen, then the thing starts to actually make sense to me now. Of course, you'd still have to solve the transportation fuel problem, and I don't believe there's any clean answer to that aside from hydrogen. But it's fascinating for me to look at this because it tells me the sort of technologies that are necessary to enable this. And it's not just making the energy initially, it's transporting it around and storing it in particular. And I won't go through the whole list of this. Many of you heard me talk about this before. But let me just stop at that point and say, whoop, here's my Bucky tube. I'm not going to talk about the Bucky tubes. I believe this problem, just listening to it this morning, where in my arguments I've been trying to leave the global climate change argument to one side, sort of disciplining myself only to use my right hind, my pro-energy, pro-business thing, and not the part of me that cares about the environment. I believe this is much more critical problem than it has been given credit for in our political debate. And that there's just no answer to this short of a major new program of the magnitude and sustained level of concentration as the Apollo program, or perhaps actually beyond that. It may take us a whole generation to get this problem solved. So thank you for your attention.
That conference, by the way, was bridging the gap between science and society, and Rick certainly had a marvelous way of doing that. I want to just bring this intro for Rick Smalley to the close by reading an email which we got last night from Nate Lewis from Caltech. Nate was a participant in the first 2 workshops we had here, and he really was greatly disappointed that he couldn't come to this one. So to quote Nate Lewis, "Please publicly extend my regrets for not being able to be there, along with my highest respect, regard, and admiration for Rick. What he was trying to do, how much he taught all of us by his words, actions, and steadfast devotion to the cause of raising visibility and constructively advancing as a scientist the most important problem of our generation. We are all indebted to him and his efforts personally, professionally, and as fellow inhabitants of this wonderful planet on which we live and want to preserve the future generations." So with that, I would like to proceed to the rest of the conference. And we're going to dispense with lengthy introductions of speakers. There are biographies in the program, and we'll assume that you'll read those biographies as the speaker is wowing us with their wonderful things. And so we'll just give Greg Urich the opportunity to come up and talk about superconductors for advanced grid solutions.
Thank you, Wade, and thank you for having me here today to present something about superconductors at this conference. Find the keyboard. So I hope you all saw the Time magazine cover, Wiring the Future, perfect for this conference, Superconductivity Revolution. There's the car that Amy was talking about, plugged into the wall, so no problems, it's all solved. Superconductivity, once a dead end, has now become the hottest thing in physics. It's fantastic timing. Oh, by the way, this was published May 11th, 1987. During the frenzy, a lot of it was centered here in Houston around Paul Chu and what later became the Texas Center for Superconductivity at the University of Houston. A lot of frenzy going around these new high-temperature superconductors, or HTS materials, as we call them. In fact, my company, American Superconductor, was founded in 1987, actually April 9th, 1987. I'm one of the founders. I was on the faculty at MIT for a dozen years there and decided to leave and follow my heart to a new company and a new industry. We're located, therefore, in Massachusetts, outside of Boston. We also have operations in Wisconsin. 263 employees, more patents than employees. We think that's a very important part of our business model, and we're a publicly traded company. So just a little bit of background on the company here. So what are these superconductors? I think many of you know about superconductors, of course, but here's a perspective. They were discovered almost 100 years ago. In an early form, mercury was the first one to exhibit the phenomenon of superconductivity. Perfect conductors of electricity if it's direct current. There is AC losses to deal with if you have an alternating current system, of course. They require cooling to cryogenic temperatures to get into the state of superconductivity. And as a result of that, there's only one key market for superconductors today, outside of the physics accelerators and so forth, and that is magnetic resonance imaging, medical MRI, and some NMR spectroscopy as well. They use low-temperature superconductor, or LTS, metallic wires in those systems. Why not cables under the streets or across the country, as Rick Smalley was looking for here? Too costly to cool them. They require liquid helium cooling. I just can't afford it. Everybody's run the numbers on this umpteen times. It doesn't work. So the excitement in 1987 and 86 was all about the new ceramic high-temperature superconductor materials, which still require cryogenic cooling, but are now able to operate at 5 to 20 times higher temperature than the old low-temperature superconductors. So that changed the economics of cooling. Thank you very much. It's great. Oh, by the way, there's ceramics, and ceramics are brittle. How are we going to make wires out of ceramic materials? That became an early key question. It's one we took on at my company. Well, there's a history here. Glass is a ceramic material, inherently brittle raw material that was converted into a valuable, robust product we all know and love, optical fibers. In a similar fashion, high-temperature superconductors, brittle ceramic materials, have now been converted into another robust, valuable product, HTS wires, zero electrical resistance with DC. It's fantastic. Zero resistance means if you have a system that is using direct current, such as DC rotor coils in a generator, you're going to get more of your product, electricity, for every unit of fuel you burn because it's going to be a more efficient generator. Motors, the same thing. Less fuel to go from point A to point B if you have a high-efficiency superconductor ship propulsion motor. That's terrific. I'll tell you what, though. The market doesn't pay for efficiency. Sorry to tell you that. The market doesn't pay for electrical efficiency. Just won't put the bucks on the table for it. I've tried, let me tell you. So how do you sell superconductors? What benefit does it bring to the market? What's the value proposition? And beyond electrical resistance being zero, the value proposition goes into power density. It's the ability of the wires that we make today at American Superconductor to carry more than 150 times the electrical current of a copper wire of the same dimensions. And the good news is the power density of these wires translates into the components you make with them, which translates into the economics of the systems that you used to make, or that you make with these wires inside. This photograph shows you, this very blurry photograph, shows you copper wires that have been bundled together, typical industrial conductors, 3 of them bundled together here. And here are 9 of the flat tape-shaped wires that we make at American Superconductor, HTS wires. These 9 wires match all of the power that you can carry in this set of copper conductors. So that's power density. I'm going to pass around, better say this here first, pass around this little lucite block, which has only 1 of the copper conductors and 3 of our HTS wires inside. And I ask you to look down the end here. You can barely see the HTS wires. That's 150 times power capacity advantage. So that drives systems economics. That's very important. How does it drive systems economics? Let me show you this graphic on ship propulsion motors. It turns out that 100% of cruise ships built today use electric motors to directly drive their propellers. And the big green one that I show you on your left-hand side here is very typical of the motors that are used in ships today. The Queen Elizabeth II had two 44-megawatt motors, bigger than this one. The Queen Mary II had a maiden voyage 2 years ago, had four 21-megawatt motors that look like this. So what does superconductivity do for you? Well, you can see it. A 36.5-megawatt motor weighs 300 tons, copper inside on the rotor and stator. Just replace the copper rotor coils with HTS rotor coils, and you shrink it down to 75 tons. I'm showing you a graphic here because my presentation is not going to be about ship propulsion motors, but this is not theoretical. This is not a concept. We're manufacturing today the 36.5-megawatt motor with our HTS rotor coils inside, and it's 75 tons. So this is a real thing today. Less than half the size, less than a third of the weight. Higher net efficiency. You have to pay for the cooling, but the efficiency of the pole sets in here are so high that you have higher net efficiency. And they're so powerful that we actually change from an iron core motor that you typically find to an air core motor. And that allows us to shrink down the side. No cogging torque, no noise, it's inherently quieter. A lot of advantages and value proposition. The higher net efficiency, I look at as a byproduct. Oh, Mr. Customer, by the way, in addition, you also get the higher efficiency. And that's the way you sell products today with high efficiency in them. Another way to look at this is in terms of the HTS advantages in power density in the grid. If you look at an urban area, you're going to find the transmission lines coming in. Some people don't like to look at those. Some people worry about electromagnetic field effects, etc. Well, go underground. You take up a lot of space. You have to haul away the earth, put in special thermal sands because these copper or aluminum wire conductors heat up from resistance. And it just takes a lot of room. The same amount of power as you put through these lines or these underground cables can be carried by a small HTS three-phase cable system. And that leaves a lot of real estate available now for additional power transmission cables or distribution cables, sewer pipes, gas pipelines, telecommunications, what you like. And that real estate underground is very valuable. So this is a real advantage here for these superconductors. So what about the markets for superconductors? What are they? Well, very simply, it's wherever large amounts of power are involved. We're not looking at little motors in electric cars, at least not yet. Maybe in the future with quantum wires, maybe with Bucky tubes, etc. Maybe, we'll find out. But the markets today for superconductors, wherever large amounts of power are used. So transportation, the transmission grid, of course, magnetic separation, defense applications will be another one, of course, already started. This is truly a disruptive technology, or a technology that disrupts businesses, maybe is the way you really should say this, because it leads to lower systems cost. By shrinking down large electrical systems, whether it's motors, generators, or transmission systems, you take out cost. And that's really important if you're going to get a technology into the customer's hand, get it adopted by the customers. Higher performance, we talked about some of those aspects, including electrical efficiency, and smaller size. This is the description of disruptive technologies. You have it in superconductors. So that's what we'll be looking for. And I wanted to peel back the onion a little bit further now in terms of the cables. Because of the power density, we can replace all of these copper cables for, let's say, 1,000 megawatts of power transmission under the city streets with 1,000 megawatts transported by HTS cables here, typically 3 to 5 times more power through existing corridors under the streets of our cities. Lower system costs. As an example, you'll typically find in urban metropolitan areas $11 million per mile for a 345 kV copper cable system underground. With our second generation HTS wires that we're scaling up in manufacturing today, look for that to be $6 to $8 million per mile. Now I can get the conversation going with the customer who might buy this cable system. Lower voltages, you wouldn't do it at 345, you do it at maybe 138 kV. You reduce costs by taking voltages down on either end of the line of the cable system. Controllability, I'm going to come back to that next in a lot more detail. New things that are available from superconductivity is controllability in an AC network. We can make it act like a DC cable system as opposed to what you have to do today with a DC system with the converters on either side. More efficient? Maybe. You got to pay for the cooling. Probably it's break even with an AC system. With a DC system, it's probably net higher efficiency. So those are some of the points. And again, let's peel that back further, because the new capability that comes with high temperature superconductors is this controllability and something we call VLI superconductor cables. So great, we have the increased power throughput that I've been talking about a little bit, but you can also design these cables to be have a core that's very low inductance, which means that you'll have a very low impedance cable system. And that means it's going to be able to draw power flow from the surrounding network. So what you're really going to do, we're going to come and rewire Houston someday with our HTS wires, of course, in New York City and Tokyo and Rome. I look forward to that. But the way it really starts is that we're going to come in with our transmission planning team, and we have 6 transmission planners on our staff. We go in and analyze a grid, and we're going to judiciously and surgically implant maybe a mile of VLI superconductor cable in one location, maybe 5 miles over here, to take the heat off the surrounding grid so you can get more power flow through the existing assets. That's the way I think it's going to start. So I showed you optical fibers before, and that all started out in the marketplace with long-haul transmission of data and communications. And now we're trying to solve the last mile, last inch problems. It's the opposite with superconductor cables. We're going to the last mile first, or the first mile first, I guess, and we'll go to long haul later on to meet Richard Smalley's vision for the future. And it really is going to start with these VLI superconductor cables in urban and metropolitan regions. So you get controllability out of these cables. It's a coaxial design. And in fact, the shield layer of HTS wires perfectly shields the magnetic field from the core, which carries the power. And because of that, you have, again, a very low impedance cable system. That means I can buy phase angle regulators and other equipment off the shelf from a Siemens or a GE, and I can literally put these in the grid with these VLI cables and dial up or dial down the power. I can even reverse direction of flow, and this is an AC cable system. Can't do it with copper technology or aluminum technology inside these cables. So this is new. It's becoming available. I'll tell you where we're at with this. The other aspect of this is it makes the system, the network into which these VLI cables are placed, self-protecting. So that, you know, if I had a break or something later on, I can pull out my computer and show you my Power World simulation of various grids where we plug a VLI superconductor cable in a grid and then damage part of the grid. Maybe it's a lightning strike. Maybe it's a willful damage in another part of the grid. Maybe it's a hurricane. And what happens is the blackout spreads from one point to a wider area, and a lot of people are without power. But in fact, if you have a VLI superconductor cable in the system and it's not hit directly, it absorbs the extra power flow, and you can change it automatically, or you can tweak it if you wish, and keep most of the network up and running. So a lot of exciting things are made available by superconductors. Where are we at with the technology? A lot of progress over the year. Currently, there are about 10 cable projects, HTS cable projects, going on around the world today. 5 of these, as I say here, are powered by AMSC. That means it has AMSC wires inside. We're the prime contractor on a cable project I'll tell you more about in the next slide, going in Holbrook, Long Island. We've chosen Nexon's cable company as the largest cable company in the world to be the cable OEM for this particular project. But there are cable projects also in Korea, China. Ultera is putting a cable into Columbus, Ohio. It'll be energized around May of 2006. Condumex in Mexico City has our wire inside going into a cable project there. And then as you see down the bottom, 5 additional cable projects in the U.S., Europe, South Korea, and China. So a lot is going on today. 9 cable manufacturers around the world are engaged in developing these cables for these various projects. So that's the momentum of today. In the LIPA, Long Island Power Authority cable project, this is a first-in-the-world transmission voltage superconductor cable going in the grid. And it's going in their actual grid in Holbrook. 138 kV, 2,400 amps operating current, 600 meters long, so it's a first segment that goes into their commercial grid. 155 kilometers of HTS wire goes into that 3-phase cable system. It is the coaxial cold dielectric design, VLI design in other words, and has 161 kV terminations for the system. Why 161 when it's only a 138 kV system? Probably 161 is the highest, maybe 200 kV is the highest you'll ever go with HTS cables. I never see another 345 kV cable system going in the United States in the future once these 138 kV controllable cables are demonstrated and accepted by the industry. Why would you bother? So we've designed the cable determinations at 161 to test those out. This is spiral development. So we're ready for the next step, which we think will be putting in 161 kV cable system someplace here in the U.S. Commissioning of this cable is scheduled for September 2006, so it's upon us. And by the way, this photograph shows you the 161 kV terminations. They've been lightning pulse tested to 750 kV. These things work, and there's a 30-meter prototype cable in the background here as one of the early prototype tests of the cable system. So this thing will work. It's going to be exciting, and it opens up the market for cable systems. After almost 10 years of work in demonstrating cable systems of various kinds in various places around the world, the blue on the screen here represents a distribution voltage, the red transmission voltage. So clearly a lot more distribution voltage cable systems have been up and running, have been demonstrated. There have been failures along the way. There's been learning from those failures. Spiral development, once again, that learning has been used in the next cable project. And that's why we have today 9 cable companies actively engaged with 10 cable projects. This is happening. This is going to be available. And by the way, there's support at the highest levels. President Bush, in a number of speeches, has talked about superconducting power lines as being part of the solution. And at another level, the Energy Policy Act of 2005 has said that, has authorized now, such sums as may be necessary for the development over just the next 3 years of very low impedance, VLI, controllable HTS AC cable systems as well as HTS DC cable systems. So very much in line with the vision that Rick Smalley brought to this set of conferences started some years ago. It's now all coming together, and it's in the Energy Policy Act. And by the way, you probably won't use DC for the long haul. You can use VLI superconductor cables. Think about it. If you did the Empire project in New York from upstate New York down along the railroad track along the Hudson River to Manhattan, why would you go DC? There are no cheap off-ramps if you go DC. Go VLI superconductor cables. It's AC. You have an off-ramp at every substation if you like to. So in Newbridge, put in a tap there and go across the Berkshires into Massachusetts or southwest Connecticut to take care of some of the grid congestion problems there. You do it with VLI. You don't do it with DC. But let's demonstrate the DC cables as well. Believe it or not, there's not been one demonstrated so far in the world with HTS. Which brings me to the subject of blackouts. Somebody mentioned before the April 14, 2003 blackout in the Northeast, 50 million people without power. That's represented here. But there have been a lot of additional big blackouts in the U.S. and other places around the world with an increasing frequency over the last 10 years or so, particularly the last 5 years. Why is that? Are the lines breaking? Many were ice storms. Most cases, in TVA, Tennessee Valley Authority, says 90% of the cases, no physical damage. It's simply a voltage collapse. Well, that makes sense. You know, the voltage collapses, goes to zero. Lights are going to go out, folks. Why is the voltage collapsing? What's happening here? And Jimmy Glotfelty, who just came back in the room, put out this report in April of 2004 and said, you know, we studied here with Canada, the big blackout in a lot of detail. And in fact, the number one reason was failure to maintain adequate reactive power support in the grid. And when we got into a stress situation, there wasn't enough VAR support or reactive power support. Reactive power is measured in volt-amp reactive or VARs. And as a result of that, we got the beginning of a collapse that led to 50 million people without power. So we say, think VARs. And I say that primarily because we sell products with VAR in the name. But in fact, VARs is a critical part of the solution, and advanced VAR solutions are now available. We have been selling for the last 5 years reactive power or dynamic VAR solutions based on power electronic systems, advanced IGBT power semiconductors, which have been going into the grid primarily in North America, but on Monday we just announced the first grid application in Iceland, a 40 megavar system. Here's one in a DVAR in a subsystem in Texas. We have 2 right outside here somewhere in the woodlands in Houston. We have 2 in Rayburn Country Electric, southwest of Dallas. We have enough of them out there that when I give a speech, I can pick the slide that shows the local DVAR solution. This is a flexible AC transmission type of device that actually works. Is providing reliable service and voltage control for utilities, and not just utilities, wind farms as well. We can talk all we want about wind farms and photovoltaic cells and farms and so forth, but you got to hook it up to the grid. And guess what? The grid operator says, look, I can't deal with your variable voltage. You have to put a DVAR in place in order to smooth out the voltage and regulate it so that I can have reliable power going through my grid. And so we now are serving over 700 megawatts of wind power in the United States and in the UK today with our DVAR systems. And power process manufacturing, same thing. Now I'm on the customer side and I see the glitches coming in the grid. You know, I'm not going to generate my own power. I have 2 transmission lines coming in, but now I put a DVAR system in place to clean up the voltage sags that normally occur in the grid for normal grid operation. And we have one at Micron Technologies for almost a year now. They got a return on investment within 3 months because it cleaned up all their voltage sag problems and gives them clean power. Their productivity goes way up and so forth, and we're looking for more orders in that area. Well, what's that have to do with superconductivity? Nothing, except that it says that there is a customer base out there for VAR-based solutions. What can we do with HTS wire technology? And the answer is synchronous condensers. HTS, or superconducting synchronous condensers. And this shows you a couple of pictures of taking our wire, which is, you know, the ceramic material I mentioned before. We've found out how to make it flexible and durable. So here we've built a saddle-shaped coil, and we stack these on one another. We make a pole set, and they fit very tightly on a cylindrical rotor, of course. And that gives us very high power density and high output in a rotating machine, with high efficiency because it's a DC rotor coil. But you have to have that capability to do this. You put it on that rotor coil, you put it inside of a cryostat or torque tube, and that gets assembled and mated with a stator, of course, an exciter on the end here to make a rotating machine that looks just like a motor or a generator, except it's a synchronous condenser that produces VARs, reactive power. And that might be packaged on a skid or in a container. Here it's in a container, and this is located in a substation in Gallatin, Tennessee, right outside of a steel mill that has an arc furnace in it. And arc furnaces are famous for causing voltage flicker. This system has been there just less than a year. It has seen more than 5 million voltage events in that period of time, an astounding 5 million voltage events, and it's taken all of it. So it's a very tough machine. TVA, so this extends or supplements our DVAR solution, expands our sales growth opportunities because within any given grid, a DVAR might be the right solution for a part of the grid. A SuperVAR, as we call it, SuperVAR synchronous condenser might be the right solution for another part of the grid. Or it might be that you have an RMR situation, reliability must run generator in the middle of a city, and it's causing pollution and so forth. You want to get rid of it. Put in a SuperVAR synchronous condenser, and you can get rid of that. So a lot of different solutions it brings here. So it really does extend our sales growth opportunities. TVA gave us an order for the first 5 commercial units, subject to the successful operation of this first prototype at the steel mill. I expect they're going to release the first couple of these to production, and I expect we'll be shipping the first commercial SuperVAR synchronous condensers to TVA by next fall. This will be the first HTS commercial product going in the grid anywhere in the world. So it's here, it's happening. And, as it says here, let's not forget, superconductors are smart materials. Or maybe they're bad materials. I don't know. How do you want to describe this? You put too much current through them, they're going to go back to become a resistive material. And you could take advantage of that in designing something called a fault current limiter. When you get a short circuit in the grid and the generator spins up, you get a current spike going through the grid. Think of these as surge protectors for the grid to limit or dampen the current spike that's going through the grid. You have mechanical breakers in the grid that normally want to open up. Sometimes they do. A lot of them get damaged over time. It's very expensive for utilities. Utilities clearly want something that can go in there and suppress or limit the current prior to the spike getting to the breakers. So we formed an alliance with Siemens in February of this year to, in fact, develop HTS fault current limiters. There have been many attempts by ourselves and others over the last 15 years, as a matter of fact. But now we have a second generation wire that we believe is the source of the solution here. So we'll develop and supply the wire, and Siemens will develop and supply the fault current limiters, and we're engaged with a number of utilities around the world in understanding what their specs are for this product. So smart materials enable new products. There is no fault current limiter with the conventional technology out there. And so this is a great opportunity for the high temperature superconductor materials. And I'll end with another slide, futuristic looking slide, just like that Time magazine slide I showed you before with that fancy, futuristic car in there. Here's another one, a maglev train, which is really futuristic, of course. But I think Time magazine actually had it right. Because Central Japan Railways had this pavilion at Expo 2005 from March to September of this year, and they showed off at this an HTS electromagnetic coil for their maglev trains. And of course it's HTS wire from American Superconductor, so it's powered by AMSC. And this is really exciting. I was actually in Japan several weeks ago. I got to ride on the train. It's been developed over a 40-year period of time in Japan, maglev trains using low-temperature superconductors. We hit a peak of 503 kilometers per hour when I was on the train, and I got to tell you, that's exciting. But I also got to see where the HTS set of magnets is going on this train, and that's even more exciting for me. They said in public announcements earlier this year that they're going to demonstrate the replacement of the LTS coil magnets on this train with an HTS magnet system, and that will be occurring very, very soon. So the future is here. Time magazine did have it, in fact, correct. What about the future beyond today? Will there be room temperature superconductors, quantum wires coming out of Rice University or other places, other advanced wire technologies? Probably. Don't know what those are today. Notice that it's taken American Superconductor 18 years to get to where we're at today. And, after a while, you've got to check the history books and say, gee, why is it taking this long? And you go back and look at semiconductors, and you look at optical fibers or Kevlar, other advanced materials, and you find out it takes about 20 years from first discovery in the laboratory to acceptance in the marketplace. Part of that is due to the advanced material. It's never been around, so now you have to develop, you have to make it into some product. That's almost the easy part. The hard part is customer adoption. And so it takes about 20 years. So we're kind of right on schedule here at 18 years with first commercial products going into the grid next year, other commercial products already being sold, small electromagnets and so forth. There will be new technologies coming along, maybe room temperature superconductors or quantum wires. AMSC will be there to take it from materials to machines to system solutions. So thank you for your attention today. If there are any time for questions, I'd be happy to take any.
Sure, let's take a couple of questions.
First cost, ROI, TCO, lifespan. Yeah, sure. First cost, ROI, TCO, and lifespan is in comparison to standard cables.
Well, once again, you have to, let's take the ship propulsion motors or synchronous condensers as a rotating machine example. You're not going to be able to charge a lot more for those machines than you get for a conventional motor. So you have to have equivalent pricing. Now, I like to say equivalent, not equal, because I want to get as much of a premium as possible, because I'm going to tell you as a customer, by the way, at your current average electricity price, et cetera, let's run the numbers. You're going to get a payback on a premium that I'm going to charge you within X years and so forth. And I got to try that angle to sell the efficiency here. By the way, it's more compact. So if you're a ship owner and operator, we talk to them and they say, I could put in 15 to 20 more passenger cabins on this cruise ship of a sort of standard volume. That goes right to my bottom line.
What about TCO, and are there higher maintenance costs?
What do you mean by TCO?
Total cost of ownership, so the maintenance and service and all that.
Yeah, one of the big problems with electrical equipment is heat. It wears out the electrical insulation, whether it's a rotating machine or a cable system. It leads to failure. We don't have the heat. So as the analysis has been done by many people, including the customer side, it's look at the maintenance cycles. Maintenance is going to be less, so therefore your total cost of ownership is going to be going down. It's a break even with the cost of the cryogenic cooling. A lot of utilities say, well, gee, I've never used a cryogenic coolant in my system. Well, they have used oil inside of systems as a dielectric fluid. They're used to pumping and cooling stations, but still it's a cryogenic. How am I going to handle that? Well, the industrial gas companies are stepping up and say, look, I'll guarantee cold. You lease the equipment from me, and I'll guarantee the cold. Give me a service fee for doing that, of course. So the business models are coming together, and it looks like total cost of ownership, taking into account efficiency and other factors, it's not bad. It's about equal.
And any field information on lifespan that you can really, show to some of these utilities and have them be comfortable with?
Well, look at that SuperVAR synchronous condenser, over 5 million voltage events, and it's been stressed and strained, I can tell you, and it's taken it very, very well. So I don't see the issue there. In terms of the cables, that's not commercial yet. We got to put the Lightbook project, the cable in place. We got to get the others in the U.S. and others around the world. We need to follow through with the Energy Policy Act requirement now to do the VLI cable and the DC cable. I would say we're looking at commercial HTS cables by the end of the decade, but not today. So we have more to demonstrate in some areas. Other places, I think the capabilities have already been demonstrated.
Thank you.
Question back here?
The bottom line question is, how long can you transfer electricity? I know that right now, with the very high voltage power lines, they're talking about up to 200 miles, could be economically transferred. Larger distances, you rather transfer fuel. With this new technology, what is your projection for the distance that electricity can be transferred? And just to make the point stronger, you talk about a country like China, where they want to make electricity in the Gobi Desert, which is probably almost a distance from California to New York to Shanghai or Beijing. So,
yeah, and in that case, they're going to 1,000 kV lines, which is incredible. They have one up, it works, so that's one way of thinking about it. I have a slide, which I'm trying to remember exactly what the distances are in it, so maybe I'll have to see you at the break to give you a specific answer. But in fact, we've gone through a lot of analysis on this. You're looking at operating HTS cable systems at lower voltage and much higher currents and going longer distances. So the answer is you go significantly longer distances with the HTS cable system. I won't quote any numbers because I don't remember them precisely here, but I can share that data with you later on. Or at the same voltage, again, you carry more power because of the higher current over also a longer distance. So I'll show you the data a little bit later if you're interested. But it's a real advantage. So I talked about the first mile VLI superconductor cables surgically implanted into urban and metropolitan regions. I really believe that's how it gets started. But when it spreads from that, I see regional power hubs. I mentioned the Empire project, which isn't going forward, a DC cable project from upstate New York down along the Hudson into Manhattan. Again, I think that should be a VLI superconductor cable. You have no issues with the distance there, even though it's AC, which is interesting. And then you have the off-ramps into other areas. If you put in those off-ramps and go over to Pennsylvania where you can generate energy remotely and then send it over the grid as electricity as opposed to shipping carbon atoms, you form what you might call a Northeast power hub. And Jimmy Gloffelty may talk about Grid 2030, the vision coming out of DOE, which in fact calls for these power hubs to be put in the Northeast, the South, all around the United States. Eventually, you connect those with Richard Smalley's long-distance cables, maybe 30, 40 years from now. So long distance is not an issue here with VLI superconductor cables, at least at the regional power hub level. And again, I can show you the exact data a little bit later.
Thanks, Greg. So is that sort of 600 meters is a small step for mankind? Okay, the next talk is by Jesse Burst. Has the moment come when and why the smart grid will reach the tipping point?
Thank you. I think I'll start out up here this morning. When I heard that we're having barbecue for lunch, I love barbecue. I love Texas barbecue most of all, so I wanted you to see all be able to see my tie and my shirt before it's covered with red sauce. So here's proof that I did have a clean shirt on when I walked in this morning. I wanted to tell you a little bit of what I do, because I think I may have a slightly different job and bring a slightly different perspective to this issue than most of the people around the table. My company sits at the intersection of technology, money, and markets. So we research technology trends to find the breakthroughs at national labs, at startups, at industrial research facilities, other sources of innovation. We research the market so we know what customers want, so we can hook the deserving technologies up with actual customer needs, things they'll pay for. And then we research investment so that we can hook those technologies up with the money they need to commercialize and get out there and really make a difference. So that's the perspective that I bring this morning. Now, because this is a research-oriented conference and we are a research and consulting company, the organizers asked if I would start out just a little bit of coaching. This is a mixed crowd and not all of you have a research background. So here's quickly 4 terms that I think will help you understand some of the research terms as we go along today. One of those is the boson layer. Now, you know about the ozone layer that protects us from ultraviolet radiation. The boson layer is a substance surrounding stupid people that prevents the bright ideas from penetrating. So there's the atmosphere, and that's that rarefied atmosphere that's populated by those lost in space administrators and the bureaucrats and the politicians, those ones who turn your grant requests down. There's expertise. That's those researchers that only pretend to have the answers. And then finally, there's the Doppler effect. And this is the tendency of stupid ideas to seem smarter when they come at you more rapidly. So I hope those will help you as we go along today. A theme that you'll hear me say several times during my talk this morning is that history repeats itself, but the price goes up each time. And we learned this rather tragically just a month or so ago with the hurricanes that hit Louisiana. And I guess the question I'd ask you to think about is, are the folks in Louisiana glad now that they didn't bother to waste that money back in 1969 when they got that first slap across the face when Camille hit them? Are they glad they didn't waste that money to make those levees higher and create those evacuation plans that they knew then they needed? Are they glad they didn't bother in 1992? Are they glad they didn't bother last year when there was a National Geographic story that very, in an eerily prescient way, explained what would happen if they were hit? So, and then I would also remind you that history repeats itself in our field as well. Here's a little look at some of the recent blackouts. And the question I think for our group today is, how high must the price go before we get the message? You know, life has the way of, as my mother used to say, of, giving you the lesson until you get it. She'll just keep giving it to you over and over again. So how hard a slap do we need across the face before we're going to take the steps we need? And here's a quote from Roger, who we'll hear later this morning. So the last big blackout was 15% of the population. Do we have to have 25% in the dark, 50% of the country in the dark? Do we need to be 5 years behind China, 10 years behind China? How high does the price need to get before we'll do what needs to be done? I want to talk about these 3 things real quickly this morning. Has the moment come? Are we finally at the moment when the smart grid is really going to take off, both as an opportunity for utilities and as a market opportunity? What does it matter, and what you should do? The smart grid is the transformation of this infrastructure by computers, electronics, and advanced materials. Just saw a fabulous example of advanced materials from Greg just a few minutes ago. So many of these technologies and these concepts have been proven already. They've transformed the telecommunications, they've transferred business computing and network, they've transformed and created the internet. So we're familiar with many of them. Now, the grid, of course, is that piece that sits in between. If you look at the traditional value chains, it's in between generation and end use. So you generate, you create the electricity, you transport it, you deliver it, and then you consume it at the end use. Here's another way to look at that. We can kind of tip it by our side. You've got generation at the top, transmission and distribution in the center, then down to the customer premises at the bottom. We're talking in the smart grid about that section in the middle, and some of the most interesting opportunities are where that grid touches either end. So where it interconnects with generation, where we convert, control, step up, step down the power, invert it, remotely dispatch it, control the power flows and so forth. And then at the far end where it touches a customer premise, where we have opportunities to do advanced and smart metering and things like demand response and other things that could really be bring big benefits to the grid and to the country. So let me give you some evidence that seems to indicate that we're at or near a tipping point. Now, there's three major drivers that we've uncovered in our research at the Center for Smart Energy, and I'll talk about each of those in a slide or two. And there's also many, many enablers, these things that make it easier for these drivers to work, and I'll mention, in the interest of time, just a couple of those as we go along. Deferred maintenance. Here's an interesting little statistic from the Department of Energy that's just exemplary. It's just an example of what's been going on. Here's the research allocations for fiscal year 2005. End use 32%, generation 62%, transmission and distribution 6%. So symptomatic of the short-sightedness and the lack of investment over really the last 30 years. Some would say longer. Some would say 40 or 50 years of underinvestment. From 75 to 2004, demand up 100%, grid spending down 50%. Now, I didn't say demand up 100%, grid spending up only 50%. I said grid spending down 50%. So you can see the kind of delta, the gap that's been going on. We're operating at capacity at many regions, and we'll have speakers later today who can speak to this in much more detail and depth of knowledge. But much of the North American grid is reaching the end of its design life. Just spent last month a little bit of time at PJM's headquarters, and Jimmy, you'll recognize this. They have this graph of their transformers, and if this is young and this is old, their chart goes something like this. All of their transformers are at the far end very old and at or beyond, many cases, their design life. So this deferred maintenance is adding up to this tremendous pent-up demand. We've had 30 years of underinvestment. Meanwhile, our economy is amazingly more dependent on electricity than it was in the 70s. And at the same time, we've had these big increases in power shipments between regions, which this grid was not designed to accommodate, and that has resulted in this major shortfall. EPRI says we need 50 to 100 billion over 10 years, 5 to 10 billion a year over what we would otherwise invest in the grid. And quite frankly, we've been living off the trust fund. You know, the mortgage is due. We can't live off it any longer, so the spending has in fact started. We're now beginning to reinvest because we have to in areas like Long Island and New York and Connecticut and many urban regions and all over the country where we have bottlenecks and congestion. So the question is, are we going to take that money and are we going to spend it on last century's electromechanical gear, or are we going to spend it on the new, smart, more efficient, more productive gear? So is the XYZ utility going to call up GE or Siemens or ABB and say, you know, as substations you sold me 30 years ago, send me 400 million more of those, please? Or are they going to be looking for state-of-the-art technologies? Regulatory changes as well. Now, in the interest of time, I'm not going to go through these. And again, there are folks here who know these very intimately. I'll just suffice it to say that these mandates that have been coming down can't be accomplished without modernizing the grid. You can't have smart metering without a smart meter. You can't have time of use and other things that have been mandated without upgrading this central piece of infrastructure that connects everything. Very powerful force, especially for utilities, you know, who've been living in a regulated environment for more than 100 years. Now, here's the third big driver, and it's one that's a little bit more long range and a little more conceptual, but it's becoming more and more powerful, and that's the realization that you can substitute silicon, computer intelligence, and electronics for big capital assets. You can reduce the need for new power plants and power lines, these things, peaking plants and spinning reserves that we construct just to sit there for that 50 to 100 hours a year when we have a peak need, just in case we might need them. We can avoid building new things by running current systems much closer to capacity. And this is not a trivial amount. Both PNNL and RAND have studied this and concluded that somewhere between 50 and 100 billion could be saved over the next 20 years in avoided costs by using, again, bits to replace iron. And the idea is beginning to gain some currency. Last year, Bonneville Power Administration announced a new policy. They call it their non-wires initiative. They are not allowed, they do not allow themselves to build anything new until and unless they've studied all the other non-construction alternatives, which are virtually always some kind of smart, intelligent solution instead. So those are the three main drivers. I also wanted to talk about this new sense of urgency. Here's a picture, by the way, of a service station in my town. I don't know how it looks in your city. I put this up recently, and one of my partners has a teenage son, and she wanted to know where that was because she would be delighted to turn in her firstborn right now for something of value. So we've got these rising oil prices, which are not directly tied, except perhaps in the Northeast, to electricity, but nonetheless it sort of underlines, puts a spotlight on this whole energy issue and this realization how vulnerable we are, and the realization that there are ways to substitute electricity for oil. And in the words of Rick Smalley, electricity must become the new oil. And so that's making it much easier to get some of the attention and policy changes that we need to move forward in this area. And finally, there's just plain old-fashioned greed. And the realization that this really has evolved into a major market opportunity. Now, I want to be fair, and I want to be sure that I say this is not like the PC revolution where we're just going to wholesale sell a whole bunch of devices to people who had never had anything, or where we're going to rip old stuff out and put new stuff in instead. This is upgrading a moving train. And as we did with the telecom infrastructure, we didn't shut it down and start over. But as we did with telecom, we will upgrade this grid of ours, transform it into the modern system that we must have to remain globally competitive. But it will be a gradual revolution by evolution. A lot of capital is migrating to energy technology. It's the flavor of the month in Silicon Valley and other pockets of venture capital. Bellwether firms, the famous firms, are now migrating to this. We know this because we work for a lot of investment firms who are looking for opportunities and hire us to help them, figure out where the best spots are. And a lot of specialists have emerged, and some of them have been around long enough that they have track records now. Global Environment Fund, which sponsored some of our most recent research, has been around for 15 years and has an excellent track record investing in these kinds of clean and smart technologies. Now, it's kind of cliche to make fun of utilities and agencies as behind the times, and some of them are very conservative, and that's how they should be, frankly, but many of them are also getting on this bandwagon, working very hard, putting their own research in, joining research alliances and consortiums, and really testing and trying cutting-edge stuff. So Con Edison, AEP, Duke, Excel, I could go on and on, BPA TV, all of them really beginning to get on board and work hard to bring these needed improvements and efficiencies out and commercialize them. So we could be on the cusp of a new era, just as when the telecom was deregulated in the mid-'80s. We could never have, before that, your choices were touch-tone or rotary, and then they had that amazing innovation, the Princess phone, where the dial went into the handle, and that was basically AT&T's only innovation over 20 years. And then we were deregulated, and then we had, PBXs and cell phones and calling plans and fiber optics and just all the amazing explosion. And think about the customer choice that's out there in the phone world right now. All the different opportunities you've got to create and design a telecom that's just what you need. And then think about the fact that there are, in most cases, no such opportunities right now in electricity, and yet our national electric bill is more than twice our national phone bill. So we spend more than twice as much on electricity as we do on phones, and yet think of all the competition and effort to create good phone and new innovative phone products, and virtually no competition to give us new innovative electric and power products. I suggest that may be about to change. And as a result, we've got this massive market. Now, here's some figures from the Center for Smart Energy. Our estimate of 2,000 sales of electric power infrastructure equipment, just capital expenditures. We estimate that of this, and this is everything, old stuff, old style stuff, new style stuff, about $45 billion is addressable by smart energy technologies. That doesn't mean they're selling it all yet this year, but the percentage goes up each year. And many people think this underestimates it by quite a bit, because this does not include operation and maintenance budgets, and those budgets often include replacement or upgrade of equipment. History repeats itself, and so do scoffers. This first one is from somebody who said to Henry Ford lawyer that the automobile is just a fad. Then Thomas Watson, the man who founded IBM, even he didn't get it. He said he thought maybe they would sell 5 computers when they switched from office equipment to computing. Ken Olsen famously said there's no reason anyone would ever want a computer in their home, and then he watched over the next 10 years as personal computers destroyed his company, and it no longer exists, was eventually absorbed into Compaq. And then I hear from a lot of the utility executives and others that, we've been talking about a smart grid for 25 years, and it's always 3 years away. And when I hear that, my response is that, 25 years is about right. That's what it takes typically. You see, the gating factor is not pace of technology innovation. The gating factor is the ability of humans to adapt to change. Now, we learned that back in the 80s from Alvin Toffler with future shock, but we actually learned it 120 years before that with the German philosopher Schopenhauer, and he's the one who proposed the history of a great idea. And I'll paraphrase it here, but when it first comes out, it's ridiculed as absurd. And then when it gets a little closer and people think it could be adopted, then it's attacked as dangerous. And at that point, it's then accepted as self-evident. Everybody gets on the bandwagon. And I'm going to propose to you that the modernized grid is now self-evident. I have another slide. I didn't bring it with me today, but it brings up the cover of about 2 or 3 dozen reports authored by all the different constituencies, the consumer protection groups, the environmental groups, the laboratories, the scientists, the utilities themselves, the trade alliances, the business groups, all of them calling for improvements to the grid, talking about how essential it is for this to be upgraded and improved. So we've got the consensus now that something must be done. When the moment comes, new markets emerge. Personal computers, internet, telecom, airlines, retail. I could have gone back much further. We could have talked about what happened when steam power came. We could have talked about what happened when railroads came in and made things like Sears Roebuck possible. But here's some that we know from our own lifetime. And when the moment comes, leaders emerge as well. And often these leaders get the lion's share. Companies like Microsoft, Intel, Walmart, which in this revolution of retailing. So has the moment come? I'm going to say yes for the country that sees it. Now, we work with a lot of foreign companies, including companies from China, who are over here to source technology. They're looking for joint ventures and products they can buy and install there. But their pain is even more intense than ours. Step off the plane in one of their big cities, and within 10 minutes, your eyes and your throat are hurting. They have these factories that are their lifeblood, forced to shut down because the power's out. So they really get it, and they're centrally planned, so they can say, "Thou shalt," and it gets done. And they have said, "Thou shalt begin building state-of-the-art grids, and thou shalt begin to use renewables," and they're moving forward very aggressively. So it may not be us. I certainly hope it is, but for the country that seizes it, it's here right now. I want to talk a minute about how it doesn't matter. I'm going to talk about the future, so I'm going to coach you through some futurist vocabulary that I think will be helpful as well. Forelash, that's the backlash, except you get tired of it before it happens. I kind of have forelash for the hydrogen economy. It's kind of tired of hearing about it. Anticipation, that's the when something doesn't live up to the hype, Prestalgia, that's that wistful longing for something that hasn't happened yet. I grew up reading Popular Mechanics and Popular Science, and they always had these gyrocopters, and I'm very prestalgic for for the world of personal gyrocopters. I'm not sure if I'm going to make it or not. And Vujade, kind of like deja vu, but it's the eerie feeling that you've seen something you never want to see again. So what does it matter? Well, I'll just put it very simpler. The smart grid matters because it is essential to all these other things we want. So if you believe in clean, green energy and renewables, how are you going to get that power from where it's made to where it's used? How are you going to get that wind power from Montana and South Dakota to Chicago and Southern California? If you're interested in national security, if you don't want us to be dependent on foreign oil, do you know, I'm on the Advisory Council for Pacific Northwest National Laboratory, and they do some great research in this. We now send, I think it's $325 million a day to the oil exporting countries, many of whom, like Venezuela, use it to finance, campaigns against us. $325 million a day. So politics aside, whether or not you feel that some of those countries don't have our best interests in mind, that money never comes back. It doesn't stay in this country, doesn't get reinvested, doesn't create new jobs. It just goes away forever. So if you'd like a grid that's resilient against attack, whether it's a Katrina or a terrorist attack, we must have this smart grid. If you want to see us be globally competitive, we will never be the sweatshop for the world. We will never be the low-cost manufacturer to the world. We'll never win that way. That's China and Thailand and so on. We could become knowledge leaders, and that requires computers. To the extent we retain our manufacturing, it'll be silicon-driven. It'll be robotic factories and process controls and other things that require reliable, cheap, digital-grade power. And I can tell you some sad stories of companies leaving the United States and building factories. Here's one story: built a factory instead of the Midwest, built it in Germany. Imagine losing to Germany. But the deciding factor was their power there was reliable, and they could not get reliable power. They had a robotic assembly line, so they had to put up basically their own little mini power plant here in the United States if they were going to be sure that not to spoil these materials and lose the batch and have to send everybody home. And that was what made Germany less expensive, and that's where they built their new plant. Power outages are costing us $100 billion a year, according to EPRI. So, clearly, it's just essential to our progress. Just a quick reminder about the importance of infrastructure. I could have put other things up here. I could have put the telephone system. I could have put the original grid, which one of the engineering academies called the crowning achievement of the 20th century, the single greatest engineering achievement. I could have put up rural electrification and so on. But here's a couple of good reminders that from time to time, things change, and we get this need to create an infrastructure. And so far in history, we've been smart enough to make that investment, and we've benefited then for decades to come. We've enriched ourselves, and we've gotten a competitive advantage over other areas that didn't have that foresight and didn't have that political will to make this investment up front. We need a similar investment in the grid. It's essential. It's, literally the platform for future prosperity. So I want to come back to Rick Smalley's idea of energy in abundance and just, paint for you the vision of what this world could be like if we did have cheap, inexpensive electricity for all. So imagine a world where consumers, where the environment gets better every year. That's one of my personal goals. And I want to retire early, so I'm getting a little worried. Because I want to live in a world where things are getting just a little bit better every year, not a little bit worse. And also a world where devices do the thinking. We don't have to expect the consumers to come running home and say, honey, log on, we've got XYZ Utilities got a sale on kilowatts, they're half cent off, we got to stock up on. I don't see that happening. But we can build devices, and we can do it right now, that can do that mediation for them, can respond to grid events and do demand response and so on. Imagine if energy is inexpensive and ultra-reliable, and then your business can locate wherever it wants to be and doesn't have to move to some kind of low-cost power. It doesn't have to worry and doesn't have to have the backups and the billions, about $6 billion, if you count uninterruptible power supplies, that we spend on backup supplier. Had lunch with the guy who handles the facilities for Verizon. He spends $35 to $40 million every year on diesel generators. And every time he has to fire one up, it pollutes the environment terribly. Also imagine a world where utilities get rewarded for making these needed innovations rather than penalized or scrutinized or criticized. And they can stop spending so much of their time and our rate money, on regulations and uncertainty, and become business leaders the way so many other technology companies are that actually help partner with their customers and lead them to prosperity. And then imagine not needing to go to war over energy. Or something like 1 million people die in India alone every year from indoor pollution. The Indian government has a campaign. It's trying to electrify 400 million people who today live without electricity. About 30% of the planet still doesn't have any electricity. So this has enormous implications for us and for the whole world. And for us, it's really, are we going to be third world, or are we going to lead the world? So what should you do? Here's your number one thing you can do to make this happen. Get rich. So I'm asking you, for your country, please get rich. Here's why. We've got to combine green and gold. We've got to find ways to make profits from doing the right thing, from environmentally benign or environmentally beneficial things. We have to attract entrepreneurial energy. Amy gave us some good scarce statistics. I've heard many over the last 6 months. Many people think it's even worse than we think, and we're only going to get out of this by innovation. We must have private sector capital. I mean, you've seen the budget fights now. We can't afford to pay for all of this with tax dollars alone. So we've got to help companies and communities do better by doing right. You can do that by advocating the policy change that will unleash this smart grid and similar things. You can encourage and invest and assist and join and start energy technology startups. There's nothing more important than to attracting capital, both the governmental kind of capital and private sector capital, than success stories. So what we need more, even more than we need ideas and more grants and more funding, we need more success stories. And that's kind of like ringing the dinner bell for entrepreneurs and investors. And they'll come running when they see that success. And it creates this virtuous cycle of more innovation. The other thing you should do is you should get involved. I won't pause and describe these, but please feel free to get in touch with me. Hand me your business card if you'd like more information. I belong to some of these and be happy to put you in touch with others who are doing valuable work. One of the key missing ingredients is coordination. We've got a lot of these little islands of innovation happening around and no real, despite the best efforts of the DOE, not yet one sort of cohesive, coordinated system. And we need that badly, and I hope that you'll get involved. And then finally, get informed. This is a little bit self-serving because I'm going to tell you about stuff we do, however, not too bad because it's all free. We do have a smart grid white paper, and I believe they were going to have copies outside. They were sending some from Washington, D.C., so they may be outside. If not, hand me your business card, just write white paper on it, or email me at jburst@centerforsmartenergy.com. Happy to send you the PDF file. It's all about the investment in entrepreneurial potential in this new power grid of the future. We also do a newsletter and a website. It's free. Feel free to visit smartgridnews.com, type your email in, and you'll get the free email summaries. And, of course, I'm always delighted to continue the dialogue. And here's our website, my email as well. This is the center of my life, my professional life. So I'd love to continue talking with you, exchange information any way we can. I'll pause. Do we have time for a question or two, or are we running over? I'll take a question or two, and then I just want to come back and summarize real quickly. Nobody needs money? Usually, at least I get that question, sir.
How much do you think the current regulatory environment for controlling electricity in the grid gets in the way of doing anything smart?
How much does the government get in the way of doing something smart? It's a big, big barrier. I was just in conversation with the Apollo Alliance. They called to recruit me to their cause last week, and they were talking about their strategy, which is they're going to keep an office in Washington, D.C., but they're not going to try and hit their head against that brick wall. And to be fair, there are some useful provisions in EPAC, the Energy Policy Act of 2005, but they're going state by state. And, you know, that's probably how we're going to eventually get this Gordian knot cut through and moving forward. There's not 21 states with renewable portfolio standards, not the total solution, but one small step towards. And there's more and more progress being made on really educating regulators so they understand what they need to know to make the right decisions on behalf of their constituents. So I think there's a big hurdle, but we are chipping away and progress is being made. Other questions before I wrap up? Good. The moment has come for this smart grid for those who sees it. You know, it's sitting right here. It's well tested and proven. Sales are going up. It matters because it's the difference between the third world and leading the world, and that's the choice we have as a country. And how you can participate, you should get informed, you should get involved, and most of all, you should get rich. Thank you.